My name is Gerald Thomas. I'm from the Milwaukee School of Engineering. The title of my talk is a Decision Process Toolkit, and it will be about a brief introduction to field theory of games. And the toolkit is in preparation for a course that I'm giving in the spring on the subject. My name is Gerald Thomas, and I'm going to talk to you today about some work I've been doing over the last year. Some of you may know that I've been interested in the theory of games and specifically how to extend game theory to be a dynamic theory. And by game theory, I mean the classic theory of von Morgan and Morgenstern. So in the last year, my idea was to extend the concept, teach the concept to students. And I'm at Milwaukee School of Engineering. My thought was to create a course that would explain to engineering students this new theory, okay? Now the problems are, these are undergraduates, typically juniors and seniors. They have a background in calculus, probably not differential equations unless they're electrical engineers, discrete math unless they're electrical engineers, but the software engineers, computer engineers typically know that. So in an MSOE, one of the challenges is mathematics is still fairly new. So in teaching the course for this group, I have to first of all explain to them Mathematica, then I have to explain to them game theory, then I have to explain all the things I forgot about in calculus and physics, and of course I can't do any of those things all together. So the idea was to create a toolkit because engineering students they like little toolkits. They don't necessarily do their electrical engineering work by solving Maxwell's equations. They do it by using SPICE or some other technique. So they're very used to using tools, and by using the tools and practicing the tools, they then ask the question, well, what does this all mean? So that was my approach, is I was going to walk them down this garden path, and by the time they were finished, they would actually realize, oh, by the way, I now know Mathematica and I now know game theory, and I've actually applied it to some problems that I really find of great interest to me, whether it's Pokemon or, which I've done a little bit of this type of course before with them, so I have some experience about the kinds of things that they're interested in. So let's see if I can get this to go down. Sometimes I've had trouble with this thing. Sorry. Oops. Probably just not being patient. So, first of all, what do I mean by a dynamic game? So I have to explain to them a whole bunch of things I'm not going to tell them, okay? So these are things that get initialized in the cells. They really never have to look at this. The very bottom is a list of games, it's sort of off the, which they probably will look at. But I can start off with the idea, first of all, I have to explain to them what a game is. And then those of you, probably you do know what a game is. For you, I have to explain what do I mean by a dynamic game. So what I would normally do, like to teach in mathematics, I use Wolfram's really elementary book, and I do the little baby steps. For games, I'm going to do, for this talk, a baby step and talk about a game that everybody here knows. Everybody is aware of tic-tac-toe, right? And of course, everybody knows that there's a solution to tic-tac-toe. What you probably don't know is how to formulate tic-tac-toe as a game in terms of the language of von Neumann and Morgenstern. Because the way you play tic-tac-toe is you put an X someplace and they put an O, and you put an X and they put an O, and there are different moves, right? you need to reformulate that game so that each player makes one choice, and the other player makes one choice. That choice is like a rule that explains exactly what I should do at every move, no matter what happens. Okay? Now, so what are those choices for tic-tac-toe? Well, I chose it because you can look this up on Wolfram Alpha. And Wolfram Alpha tells you that there are actually 9 choices for X and 9 choices for O. And they sort of are labeled by the places in the diagram, but they don't necessarily mean that's your move. It's just a way of explaining what the play is. And for the first person that moves, there's really only 3 choices. The choice is essentially a here or a here or a here. So we're in the middle, in a box, or a corner. But for O, there's all 9. So in the game theory context, this is a 12-dimensional space. And if I start the game and I know nothing, I don't start in an equilibrium point. So then there's usually hand-waving that says, well, after you play long enough, that's where you'll get to. In a dynamic theory, that's not exactly the right answer. In a dynamic theory, you start someplace with some boundary conditions. You may fall into the hole as an attraction, right? Or you may circle around it, or you may come zooming in and zooming out. There are many cases that you would have to walk through, and it would depend upon the details of the dynamics. So in creating a theory, what you're doing is saying it's not a theory of a point, it's a field theory, i.e., it matters where you are in the space. So I wouldn't bore the students with this, but since this is a Mathematica conference, I have to explain the approach I take a little bit, which is in a 12-dimensional space, thinking of it as a fluid flow, and assuming that the dynamics are sort of nonlinear, which they typically are, I would have to solve partial differential equations in a 12-dimensional space plus time. Can I do that in Mathematica? No. I can do it in 2 dimensions or 3 dimensions. People who design study airflow have a simple solution to the problem that's been known for a long time, which is I can't solve the problem exactly, but I get a great deal of insight by imagining that, like, I want to do fluid flow. I think of colors of smoke, right? And I watch the smoke, and that tracks the flow of the fluid, otherwise known as streamlines. So I can write down equations for the streamlines, and so I could ask them to do that. If I can do that. And in a 12-dimensional space, I can write down flow equations, follow the streamlines, and for each possible strategy, I get oscillations. And if I look really carefully, I'll see some strategy doesn't vary. I see this strategy here is oscillating, and I go into the details of tic-tac-toe. Those are the equilibrium strategies, in fact. But what I'm actually seeing is, because I didn't start at an equilibrium point, I don't stay at an equilibrium point. Is this relevant to other things that we do? I spent a lot of time in software development as a manager, and I can tell you that although there are stable systems where you believe that you're going to deliver software on a regular basis, customers come in with wild requests, and there are always these oscillations. You're always doing this oscillation. You're always taking a system and disrupting it, and your question is always, after the disruption, what happens? Well, I'd like to do one step better than streamlines, but I can't go to 12 dimensions. So a very natural choice in a game that has 2 players is that rather than have a streamline, imagine that I could follow a stream in the subspace for one player and the stream in the subspace for the other player. So each player owns a set of strategies, and The other player owns a set of strategies, so I could imagine doing a surface of these two streamlines and watch that over time. A caveat in all of this is, although I want to talk about dynamic systems, I need to build up to dynamic systems in a kind of a systematic way. And like if I was looking at weather, I can look at all the possible things that could happen in weather, but even if I'm looking at a hurricane, the flows can be stationary. So I'm going to talk about stationary flow. It's dynamic in the sense that the particles are moving in time, but the rate at which they move is stationary. But doesn't mean it's simple. There can be vortices. I can still have lots of interesting effects. So if the students get to this point and they understand, oh yeah, I'm moving in space, I can talk about a system that's dynamic, and well, one of the questions I might ask is, I have to learn game theory. So in doing the dynamics, I would have to say, well, I said it's 3 choices for one player, 9 choices for the other player, so there's a game matrix. And the way game theorists solve the problem is they use linear programming, and one trick is to make a symmetric game where this is the game matrix here, and this is the same game matrix there, and I introduce a fictitious player, so I now have 13 dimensions, and this is a nice anti-symmetric tensor, and I might point out to students that anti-symmetric tensors are not uncommon in areas like general relativity and electromagnetism, and this looks exactly like the field tensor for the electric and magnetic field, and you can go back and look at the geometry, and yeah, you can have electromagnetic fields in 12 dimensions. Okay? And rather than solve the linear programming problem, you can say the rate at which flow changes is this tensor times the flow, and that's the acceleration. The tensor times the flow is 0, the acceleration is 0, that's your stable point. When the tensor times the flow is 0, that's the null space of this matrix. Now it's a little mathematics. The null space of that matrix is the stable point that you get in linear programming. So this is exactly the same as the max-min solution for game theory. So okay, I get that. So am I done? Well, in a dynamic theory, you're actually not done. There are a bunch of problems as soon as you decide to open up the hood. One of them is, if I have an electric field and if I have a magnetic field, these are analogies, but if I have them in the 12-dimensional space, I must have things like Coulomb's law and Ampere's law. And even if I'm talking about things that are stationary, I still have to consider those effects as part of the boundary conditions. So I will introduce them to some boundary conditions and some possible choices that they might make. And then there are a number of other questions that you have to deal with as a dynamic theory, which you don't have to deal with in traditional game theory. In game theory, the actual payoff value doesn't matter. Because if I add a constant to the payoff matrix, it's a higher payoff, but the max-min solution is the same. Think about it. Again, I'm going to do the physics analogy. If I have a magnetic field, and it's a nice little line along this direction, and I go exactly along that direction, the strength of the magnetic field doesn't matter, right? But if I'm a little off, I do a little spiral around the magnetic field. The stronger the magnetic field, the stronger the spiral. Now it matters. So I now have to understand how the value plays in, and if it's something that's important, well, how would you measure it? I mean, how does it show up in your game? Okay, like for tic-tac-toe, if I play the game over and over again, my time scale could be of the matter of minutes. If my game is an economic game, and I talk about let's say a political disruption where I wipe out a third of the population, that effect might go on for generations, right? And the size of the effect is now really important. Clearly, right? So there are some questions that you have to answer, some maybe technical questions you have to answer. And so they can go through all of that. They can set the model up. And in the toolkit, all they have to do, it will do it for them, is at some point you have to run the magic ND solve. And I chose tic-tac-toe because it's really a simple game. The downside is it has 12 dimensions. The reason I'm really sensitive about this thing crashing on me is it takes about 20 minutes for this game to run. But I ran it, so it's there. And when I tried to run this game initially, I had to talk to all kinds of experts here at Wolfram because the thing crashed on me. Even though it's a simple two-dimensional PDE, I found out that the solutions would just go crazy. And I didn't understand why. And I wasn't thinking that this kind of equation was a convection equation. Because I'm looking, I have no heat here. But it's a convection equation because I have a magnetic field. So I have things that circulate. Because they circulate, they change the nature of the equation. So I have to do the same techniques that you do in heat equations, I have to do here, which is to sort of regularize them. That's all under the hood, by the way. And I had to do a couple of other tricks in terms of defining variables. Once I did that, I could compute a quality measure that's supposed to be 0 to make sure it is 0. And I can start looking at some of the flows that occur. And one of the things I see is, whoops, wrong way. I look at the effort player 2 makes in the game, let's say the O, versus the effort the player 1 makes, say the X, as a function of distance along their ownership curve, their little streamline. And at the start, it looks very linear, but I now see very clearly that I get these clear convection effects. And of course, I chose the parameters to make it look really awful, right? It doesn't always have to look like that, but if you make versus given source of parameters, and the same thing, another is to look at the stream contours. Again, in a perfect world, this would look like a nice little set of rectangles, but you see all the nonlinear effects creeping in. Another thing to look at would be the actual flows in the two directions, the flow along ownership 1, the flow along ownership 2, and you see, even though I'm only in the 2 dimensions, not in the full 12, I do see the creation of little vortices and turbulent effects. Do I expect turbulent effects? Well, sure. This is not unlike a model of weather. See, cyclones and hurricanes, I would expect to see them here. They're very sensitive to initial parameters and initial conditions, but nevertheless, you can create them. Since I have a lot of engineering students, one of the things I can do, usually in the room I have a projector and I have a cord, and I can take the cord and I can say, let's talk about wave patterns. And what we've been looking at is a steady state. with no change in the boundary conditions as a function of time. But if I have a chord and I start oscillating it, right, then I really start to see the two distinctions. One is when I start the oscillation, I see a wave go down this way, I see a wave coming back. If I continue the oscillations, I set up a standing wave. That's the stationary system. But the standing wave is no longer the standing wave that we've been looking at. The standing wave is now because I did it at a certain frequency. You would expect if I change frequencies, there will be frequencies in which I get resonances and the thing blows up. So I do that to the model, and lo and behold, I can create those standing waves. I'll come back to this in a second. And first of all, I can look at some amplitude as a function of frequency. I can see, yes, I do get things blowing up. I can look at a particular strategy at a particular time. I can see this. And I can see the effect of this oscillation, harmonic oscillation of a given frequency, arbitrarily set at, I don't know what it was, at 1.1, whatever it is, and it propagates over that area. Because I'm operating in this space, I do expect that of these 12 strategies, I should be able to look at each of these strategies along this ownership surface, which I can do, and I see that there's a lot of structure. Here are the flows. Again, there's a lot of structure. And you can see the effect of the various kinds of inputs. I have boundary conditions here on the edges. They generate effects in the middle, some of which were there already as part of the original game, some of which are simply the effects of the boundaries. In that initial curve that I showed you with all the oscillations, the frequencies of oscillations now for the different strategies and the flows are quite different. So what are some of the conclusions? First of all, I believe the toolkit is, although I've done it very rapidly for this group, the course I have in mind, I have about 10 weeks to lay it out. It means I have about 2 or 3 weeks to get them into Mathematica and game theory. I have a couple of weeks to get them into the point where they could reliably understand and how to do this sort of stuff. By week 6 or 7, they should be in a situation to be able to take these ideas, apply it to their own game, and then see what happens. And then I would expect them then to stand up and give a demonstration talk in front of the class of what they found. And some of them are real fantastic gamers on the web. So they already have experience about what happens and whether it's optimal, whether it's not optimal. They understand the value of non-optimal play in the real world and how non-optimal play, when the other guy starts being optimal, then you have to change what you do and then ask, is this modeling doing what you expect? If not, is it the fault of the underlying theory, or is it a fault of your lack of understanding of the various mechanisms that go into the model? Other thing that I hope they will learn is the behavior that we're talking about is still a optimization problem, but it is not the max-min optimization problem of game theory. It's now being replaced by, if you like, a optimization problem of geometry, which is like finding the shortest path. And they will also get some idea that in finding the shortest path, when you do a problem, you tend to figure out how to explain the problem in a way that's tractable. Now, an actual game has more than 2 players often. It can have 1 million players. But many of them don't matter. So when you break it down to a 2-person game or a 3-person game, you're saying something about how to ignore the rest of the effects. In physics, you never ignore the rest of the effects. You parameterize the rest of the effects so they at least capture their energy effects. So one way to capture it is to think of those effects as cultural and capture those effects in a tensor that you can say, here's the tensor that has the effects. One part of that tensor is simply the idea of ownership. I always thought ownership would be like a symmetry of the problem, just sort of, But then I went back and I looked at like relativity. There are symmetries in space. In general relativity, it's something like a 3+1 dimensional rotation. But there are also dynamic things that are useful approximations about the way the world is. One dynamic approximation is isotropy. Okay? That's not a symmetry. It just says that in a cosmological model at every point in space, things look essentially the same if the space were modeled as a fluid. In this case, if the space was modeled as a fluid, there would be an isotropy for each player, that the strategy choices would be the same. And there would be a set of choices for this guy, a set of choices for this guy. What I didn't expect is it's the cultural constraints that determine what strategies I own. That's very interesting, right? It means I don't get to choose my strategies in some sense. The game chooses all the strategies, but other people could, with sufficient external pressure, take over ownership of things that I thought I would like to own. So what else can we learn? So I talked about steady state. This is, the path I'm going down is a path that for my students will be very familiar, which is electrical engineering path, that if I want to learn about electromagnetism, I don't study Maxwell's equations. I study behaviors. I first look at DC circuits, then I look at AC circuits, then I look at transients. So in some very weird way, game theory classic is DC circuits. What I just described is AC circuits. And for some future talk, we would do transients. When we would do transients, we would have to take into account all the equations I left out that I have in the theory, which is the Coulomb's law and the Ampere's law and the law of attraction, how things get attracted. All of those things can be put in. Some of those things actually I do put in because I need to at least see those effects. I need to put in frames of reference, the fact that reference frames can rotate. That's a real thing, right? When I do economics, seasonal variations is very important. That's a rotational effect. It's just a harmonic effect. Every year, certain things happen. So that's what I learned there. So in the end, the students will have learned how to do a theory that has both geometric attributes, cultural attributes, or constraint attributes, and we'll have a way of applying those attributes to problems of interest to them. So I think I should probably stop there and see if there are any questions.